All right, so this problem says the current supplied to an air conditioner unit is 4 amps. The air conditioner is wired using a 10 gauge diameter. So the gauge refers to the diameter of the wire. And you guys remember the greater the diameter, the greater the area of cross section, the less the resistance of the wire. Okay. The resistance of the wire goes something like this: the resistivity times the length divided by the area. Okay. It's inversely proportional to the area. Anyway, that. Okay, so the 10 gauge wire, the charge density is, see, the charge density in metals is about 10 to the 29 electrons per meter cube. And this refers to free electrons. Okay. So then there are electrons that are bound to the atoms, and that we're not concerned with those as far as electric currents go. Find the magnitude of the current density and the drift velocity. So the current density is given by N, and Q, the charge of the carriers. What are the carriers? The electrons, and the charge is E, and times the drift velocity. Okay. And the current density is I divided by the area of cross section. Yeah. So what is it that we're trying to find? The current density. So J is, N is given, the current density is I over area. I over pi. They've given you your diameter squared by 4. Diameter by 2 is the radius, and pi r squared is the area of cross section. So 4I, 4 amps, and diameter is 2.588 millimeter. Okay. So we'll do this. That's 10 to the power 6. That'll come to the top. So the current density is million amps per meter square. Okay. And that. Okay, so that's the current density. What does this number really mean? So the diameter of this wire is 3 millimeters. So the wire is about that thick. Okay, in that thick of a wire, a 4 amp current is flowing. So what this number is telling you is, if this wire were made this thick, this is a meter squared, the current flowing would be 1,000,000 amps. The side of the table. Okay. So that's what that number means. 1,000,000 amps per meter squared. Okay. All right. The drift velocity. Now that we have the current density, the drift velocity is the current density divided by the density times the charge. We just found the current density, 0.76 times 10 to the 6 amps per meter square. And N is 8.48 into 10 to the power of 28 per meter cubed. And the charge of the electron is 10 to the minus 19 coulombs. Okay. All we need is the magnitude of the charge. Okay. And so this will give you the meters. You get a meter at the top, and this is ampere is coulomb per second. The coulomb will cancel. So you get in meters per second. Okay. And so this is equal to, what is the order of drift velocities? What is, how fast, what is the drift velocity of electrons in?
Millimeters per second.
That's right. Okay, so you sort of want to have that in your mind. So this is 10 to the plus 9, and when this comes to the top, it gets 10 to the minus 3, 10 to the minus 3, and there you go. That's a millimeter. Okay. So 0.76 divided by 8.48 into 1.6. All right, so point. So that's the drift velocity. Okay, so if I double the current in this wire, made it to 8 amps, what will happen to the drift velocity? So you see, and the formula for the current, here is the current. The formula for the current is times A. The current in a wire is N. The charge density times the charge times the drift velocity times the area of cross section of the wire. When you double the current in a wire, you're not changing this, you're not changing the charge, you're not changing that. What you're doing is you're changing the drift velocity. So when you double the current, what you're doing is you're doubling the drift velocity. And how do you double the current in a wire? How do you double?
Electric potential.
What's that?
You increase the electric potential.
That's right. Okay, so here's the circuit. Here's the wire resistance. Okay, you saw that current was equal to voltage over resistance. Okay, so you're not changing the resistance of the wire. When you're doubling the current, you're doubling the voltage. When you double the voltage, when you go from 1.45 volts to 3 volts, you double the current. And when you go from 1.5 to 3 volts, what you have done is you double the electric field in the wire, and that's double the drift speed. Yeah. Anyway, that's all the physics, that's not the engineering part. So, but all right, so in this problem, they said the diameter of a zero gauge copper wire. So you see, smaller the gauge number, thicker the wire. Yeah. Is 8.252 millimeter. Find the resistance of a 1 kilometer long length of such wire used for power transmission. All right, resistance is resistivity times the length divided by area of cross section. So we have to look up the resistivity for copper. Resistivity for copper. All right, so 4 times resistivity of copper is 1.68 times 10 to the minus 8 ohm meter. The length is 1 kilometer. And the diameter is 8.252 millimeter. Okay. So the resistance of this wire, a transmission line from here to Krispy Kreme, that's about a kilometer. Well, a little further than that. Here to, well, anyway, here to Krispy Kreme is about 500 meters, half a kilometer. All right, so let's see, this is 10 to the minus 6, that gives you 10 to the 2, then 10, so 16 point, so 4 into 16.8 divided by pi times 8.252 squared. And ohms, this is the only thing that survives. This is meter square, that'll cancel that meter square. Okay. So this 1 kilometer copper wire, which is fairly thick, okay, has a very low resistance, 0.3 ohms. All right, this problem says a resistor is connected in series with a power supply of 20 volts. The current measure is 0.5 amps. What is the resistance? Okay, so this is a fairly simple problem. Again, this is just Ohm's law. 20 volts. Current is V over R. R is equal to V over I. Okay, so the resistance is 40 ohms. This problem says, what is the maximum voltage that can be applied to a 10 kilo ohm resistor that is rated at 1.4 watts? Okay, so what will happen if you apply higher voltage? You will melt the wire. Okay, so power is, okay, so we'll use one of these formulas, V times I, or I square times R, or V square over R. V over R is I, and then 1 V, then you would get that formula. Okay, so these are the formulas for the power delivered to the device. So, uh, so we have the power rating of the device, of the load, we know the resistance, and we can calculate the voltage using this formula. Okay, so power is V square over R. Okay. So the max, okay, so here's the maximum power rating, and that will give us the maximum voltage you can apply to the device. Okay. If you apply a greater voltage, you will fry that device. Okay. So that's what your electronics will have at home when during lightning storms and stuff like that. When you get a voltage surge, that's what fries them. Yep. So maximum voltage is power is 1/4 watts and 10 to the power 4 ohms. So this is 1/2 volts. So max volt is 50 volts. Okay, so a heater is being designed that uses a coil of 14 gauge nichrome wire to generate 300 watts. Okay, so remember, higher the gauge, thinner the wire. So in your toaster, that wire that you see that glows is a nichrome wire. Using a voltage of 110 volts, how long should the engineer make the wire? Okay, so power is V times R. Power is V square over R. So R is V square over power. Okay. So this would be the resistance you want is that. Okay. And what is the formula for resistance? It's rho L over area. Okay. So what you want to know is how long should the engineer make the wire. You have the area because you know the gauge of the wire. You know the resistivity because you know the material of the wire. Okay. So L equal to V square power okay. Okay, so that's how long the wire needs to be. All right. Nichrome resistivity. Okay, so we'll take it to be 1.5. Okay. So the length of the wire is, this is P, 110 volts square, power is 300 watts, area is pi d square by 4. Okay. And resistivity is 1.1 into 10 to the minus 6 ohm meter. Okay. Diameter of 14 gauge wire. 1.628 millimeters. Okay, so everything in SI units, so the length will work out in meters, okay? So let's do this. This is 10 to the minus 6, and this cancels that, so we don't have to worry about that. So the length is 110 square into pi into 1.628 square divided by 300 into 4 into 1.1. meters. So 76 meters, twice the length of this building. So you guys have seen immersion heaters. So you gotta have a wire that big, and you gotta wind it up and put it in there. Uh, so you see, the greater the power requirement, smaller the length of the wire. Okay. So based on that, you would calculate the length of the wire and then make the heater. Okay, an alternative to compact fluorescent bulbs. Compact fluorescent bulbs, you might have seen those. Those are there's little spirals that go into this normal socket. And the reason, okay, so a fluorescent bulb converts 40% of the electricity to light. The old yellow bulb, incandescent bulbs, converted only about 5 to 10%. So compact fluorescent bulbs are a good step above the old fluorescent, the old incandescent bulb. And LEDs convert 90% of electricity to light. They're the best. Okay. CFL, an incandescent bulb, and an alternative to CFL bulbs and incandescent bulbs are LED bulbs. A 100-watt incandescent bulb can be replaced by an 16-watt LED bulb. Okay. Actually, you can do better than that. Both produce 1600 lumens of light. Okay. So lumens of light is a unit of visible light brightness. Okay. Assuming the cost of electricity is 10 cents per kilowatt hour, how much does it cost to run the bulb for 1 year if it runs for 4 hours a day? Okay, so this is the wattage is electrical wattages. Okay, so cost is so see, this is a unit of kilowatt hour is a unit of energy. Okay, so cost is equal to energy use times rate. Okay, energy is power times time. Yeah. And we'll calculate the energy in kilowatt hours. Okay, so power is we'll calculate for incandescent bulb. So the power of the incandescent bulb is 100 watts, which is 0.1 kilowatt. Okay, 100 watt is a thousandth of a watt. And the time is 4 hours per day, and we're going to calculate it for 365 days per year, right? How much does it on the bulb? 1 year, 365 hours. Yeah, and so the cost is, and the rate is 10 cents per kilowatt hour. All right, so that's how much it costs you to run the incandescent bulb. Okay. So LED bulb, okay, how much does it cost to run the LED bulb? You see 16% of that, 0.16 times that. So why did we do this calculation? So you go to Lowe's or Home Depot and see if an LED bulb is $10. You'll of course buy it because you're saving $12 every year. And this is the kind of analysis that cities did. And cities spent millions of dollars and replaced all their street lighting with LED bulbs about 10 years ago, when there were LED bulbs were even more expensive. Okay. So even you will save money. You just replace all the lights at home with LED bulbs. How many do you guys have LED bulbs in your homes? You do. All right, so that finishes the